Today we are covering first greedy algorithms. A greedy algorithm is an algorithm that selects that which appears maximal. It will always go for the thing that immediately looks best. So, so when faced with a choice, it chooses maximally. If you're trying to, for example, a knapsack problem is a very common way of introducing greedy algorithms. The idea is you have a knapsack with some capacity of how much weight it can hold, and here we're saying 10 units of weight. And we want to figure out which one of these items we want to put in the knapsack. The idea is we're trying to figure out which ones we want to take with us. And we're trying to maximize the amount of value we can have. A greedy algorithm will often sort these items in order of greatest to least worth, which would be this one first, second, third, fourth, and it will just put them in the knapsack in order. So one will get put in, now the knapsack's weight is 7, and then can't put 5 in because it goes over 10, can't put 4 in, it goes over 10, so this one gets put in, so that gets 2 get put in there, and the total value in the knapsack is 54. Now, this isn't the optimal solution. Optimal would be 40 plus 25, 65 being greater than 54. So greedy algorithms are not always optimal. They will not always find the best solution. Some algorithms do, some don't, but they do find it quickly, as opposed to an exhaustive search or many other algorithms. They are quite quick. That's the whole thing, is they will find something that's often good enough, is the idea. If you're using a greedy algorithm, it's when you're okay with good enough, not best. So as well as that, they are fast, but suboptimal, or can be suboptimal. Now, for the knapsack problem, the score by which you sort these to figure out which order you want to take them can change. This one was very simple: sort by value. You may also want to sort by value efficiency, as in to find the ratio between the weight and the value and sort by that. In that sense, you are creating a utility function. You apply to all of them and then sort. Greedy algorithms being a form of agent in terms of AI. Yeah, nothing else to cover that. Very simple problem, but also has very other nice teaching problem. Also, interesting enough, good way to demonstrate genetic algorithms. If you have an algorithm which will change what it picks based on some variables, and you make a bunch of those, all different variables, and you want to find out which one is best to find the best value, you can do that using genetic algorithms. Video of that on computer file, if anyone's interested. I won't get into it. Okay. So the first algorithm we'll be going into is called Kruskal's algorithm. And it's an algorithm to find a spanning tree, or a shortest spanning tree. So a spanning tree, is a tree that represents all nodes of a graph, but not all of its edges. So it is take in a graph and spit out a tree which contains all the nodes and contains a subset of its edges. The idea being you want as few edges as possible to form a tree. It has to follow the rules of a tree, mainly being it can't have any cycles. So in this graph, you see it's a big old cycle here. Can't be having that in a tree, so at least one of those, say this one, would be thrown out. And that's just if the graph was this triangle and we ignored all the rest. That would be an example of a spanning tree. So a spanning tree is a subset on edges, but contains all vertices. Kruskal's algorithm specifically will find the shortest spanning tree. And in this case, shortest, we are going by weight. So we will look at all the edges' weights, and we will try to find the spanning tree, which the total weight, if you add up all the edges, is the lowest. So shortest and spanning tree has lowest edge weight sum. So we go through this. Kruskal's algorithm essentially will go through all of the edges, order them by weight, ascending. So you have the lowest first, and then it will just put them into the output pile of wherever we're storing it. We're not going that deep in, but we'll keep the ones which will work, and we'll go top to bottom. So if we do this, we will keep 1. Oh, that's a bit difficult to read. Let's increase our pen size. That's better. So we'll keep 1. That edge stays. 2, C to I. This is here. We'll keep that. F to G. I'll put a tick to keep track of what we've done. F to G is here. We'll keep that. A to B is here. We'll keep that. C to F is here. We'll keep that. C to D, this one, we'll keep that. H to I is here. Now if we keep this one, we've now made a cycle. This is not a valid tree, therefore we cannot keep HI. We will not keep HI. AH, that doesn't make a cycle, we're good. BC is here. If we add this one, we now have a cycle going this way. Don't want that, so we will not keep BC. DE is here. That's good to keep. EF is here. Again, cycle. There are multiple paths. If we kept that, there'd be multiple paths. For example, to E, we could go GFE, or we could go GFCDE. That's not allowed in the tree, so we do not keep that. Same for BH. Same for DF. All of those would create a cycle. None of those are allowed. So this is the shortest spanning tree for the underlying graph. Fairly simple. Double check I've got that right. Yes, that's good. Very simple algorithm, but you can see here that the greediness is going for the best outcome. Best outcome for this is lowest number. So maximal is maximal based on what we want, and we want the lowest. Hence why it chooses lowest first. And you can always be certain that this will find the lowest because it goes by order. Dijkstra's algorithm, moving on. This is a multi-purpose algorithm. You can be used to find a path between any two nodes. If we are at A, we're trying to find G. Let's change color. And we're trying to find a path to G. We can use Dijkstra's to do that. However, it can also be used to find something called, there's a bit of a mouthful, so let me make sure I've got it right. Okay. Single source, shortest path. So the idea is here we choose a source. For this example, we are going with A. So we choose a source, and we will maintain. I've just realized I forgot to prepare something. Oh no. I'll go in a second. We need to find this shortest path from A to every other node. Which means essentially we want to go through the graph and figure out if we're going to get to H from A, how do we do that? From A to F, how do we do that? A to G, for every single node, we want to find it. Now, I need to import some, not import, but copy something over to make this easier. If I have it saved. I do. But not in the way I was hoping. Good. Dang it. Okay, one moment. Time to go to my example so I can copy it over. It may take a moment. For some reason, my output is going very slowly today. Push, push. You. Copy that. Go out. Go back in. Hopefully this works. So Dijkstra's works on the principle of choosing the whatever we see as the shortest route. So it will go from its source, A in this case, and it will expand along whatever path we know of which is shortest. First off, that's A. A being shows where we're here. And if I do this, there we go. Good. Now I just want to delete this. Oh no, it's a single thing. I can just do that. Good. So it works by following along the shortest path. So it will explore A and discover B, C, and D because it knows where they're there. And because we have this in memory, we also know what all the nodes are. We just don't know their distances from this. This syntax, this is infinity. At first, we don't know anything about how far it is away from our source, so we have it as infinity. Also ignore these, copy this from prudence thing, but I'm using the side. And the second thing, the negative, will be updated over time to show where the path from is. Okay, so the structure we're using in the data structure is called a priority queue, which is essentially a sorted queue. Queues normally they will deliver things in terms in the order of the first to come is the first to be served, as in an actual queue. Not always what's good though. Here we want to actually sort it, so while it will still maintain that order for things of equal priority, things of greater priority, which is those with lower costs, should be sorted. Should be seen to earlier, and you'll see how it updates over time. So we're starting with A. We expand A. We discover B, C, and D have all have these costs. So I go through. B has a cost of 5, and it comes from A. C has a cost of 7, coming from A. And D has a cost of 10, coming from A. Now, this doesn't have to be resorted because it's still in order. So, B, we expand B next. We're going over here. In fact, I'll put a little thing here just to show we've expanded them. B will discover H. H will have a distance of 5 plus 10. So down here, up this to be 15. This is not going from A, it's going from B. So it costs 15 to get the H from B. Haven't been there though, so we're not going to actually mark it off. The next one that hasn't been explored is C. C being here. Now C can get to H by a value of 2. We have to add on the 7 because this is the total cost, which is 9. So C actually has a path to H, which is 9 better than the 15, so we overwrite it and say C. Similarly, it can get to D by a value of 9. That's better than what we had, so we overwrite that from C. We also have E. E is here by a value of 14 from C. That's everything C has access to. We mark off C that we've explored it, and then we move on to D, which is the next one. No, before we do that, we have to reorder. This 9 has greater priority. Put this back in order, like so. So this 9 will be done before E because it has a lower cost, higher priority. D was there first, so it gets done. D gets explored next. D discovers a path to E. That path would be 9 plus 4. That is lower than 14. 9 plus 4 being 13. So 13 from D. Also discovers G for the first time for a path of 9 plus 3 is 12 from D. And that's it for it discovers. We will mark off D. We now have to reorder our queue. Oops, wrong one. That one goes there. That one goes there. That one goes there. Next one to be explored is H. H, which has a 9 from C. It discovers a path to E plus 5. That's 14. We're not going to overwrite because we already have a shorter path than that. It can get to F by 10. So F now has a path to it from 10. 10 from H. And it discovers a path to G, which is 11. Yes, 11. Bigger than 12, so we'll bigger than 12, so we'll overwrite that. 11 from H. Now we have to reorder this again. Actual priority queue. This is all done. Typically of a linked list, so insertion, deletion is very easy. We've just explored H. Let's actually circle that. Next one to do is F. F is here. We'll explore F. F will discover a path to E, which is worse than what we've got so far. 15, don't want that. And the path to G, which is also worse than we've got so far. So we don't want that. So that doesn't get anything. That doesn't update anything. We'll explore that. Next up is G. We've already explored the two things that G has access to, so we know we already have a better thing than that. No bother. Same thing for E. We don't do that. So now what we've done is discovered the shortest path. So what we can do is starting from A. A doesn't have any drawers. We know that from A we have between A and B. So we have this. We have A and C. So we have this. From C we have D and H. And D. From H we have F and G. F and G. And from E we have D. So here we have the all the shortest paths you can take from A to get to every single node. You want to get to E, you go to C, then D to E. You want to get to F, it's A, C, H, F. So now we know for a fact, because Dijkstra is one of the greedy algorithms which are optimal, that this is the shortest way to get to every single node from A. It'll be a different graph if you want to get from B, for example. It's only for one of the nodes in the graph. We have to redo the entire thing if we wanted to get from E to every single node. That is it for greedy algorithms. So if anyone has questions on that, because I'm actually going to stop the recording and then restart it for the divide and conquer section. So if anyone has questions on that, then please post them in the chat. If not, I shall pause and then move on. Okay, I'll take that as a no. Stop recording.